Hi, class. So, in our lessons this morning, we were talking about concentrations of solutions, and we're learning in this unit about aqueous systems. And so, before we look at our solubility rules and write those down, I want to just go back to our PhET simulator and let's think about what we see in the macroscopic world when if you were to dissolve an ionic or any type of substance, really dissolving it in water, what you would see in the microscopic world, and then let's zoom in really close and look at it close up from the water molecule standpoint and what's going on between ionics and our molecular compounds. So macroscopically, here we have a container with a 1 liter of water in it, and so you'll notice that right now the concentration is 0 because all that's in there is water. So concentration, we express it in moles per liter. So how many moles of the substance are present in 1 liter of solution. So you'll notice as soon as I shake the salt in there, in the macroscopic world, you wouldn't really see anything but a homogeneous mixture all in one phase. But you'll notice that the salt concentration is rising here just ever so slightly. So I just shake some more in, and the more salt that I put in there, the more moles are in the solution, so therefore the molarity is increasing. So we see a homogeneous solution. Well, what does it look like on the microscopic level? So let's take a look here at the sodium chloride. So microscopically, if you were to look at the action that this is taking place as the salt dissolves, you see the sodium ions and the chloride ions being ripped apart by the water molecule. And that's because sodium chloride is a soluble salt. And so in this lesson, we are going to be looking at the soluble salts. Now, if you have an insoluble salt, it would not be pulled apart the way that you see here. Here you have mobile ions. They're moving around independently throughout the water. And so the reason that this would be an electrolytic solution is because there are mobile or moving ions present. The conductivity of it is going to be directly proportional to the number of ions present. So the more of sodium chloride ions that I put in there, the stronger the electrolytic solution will be. All right, so now let's look at it on the really magnified level of from the water molecule standpoint. And I want to highlight here the partial charges of water as well. And so I'm going to click on that, and you'll notice that the red oxygens have a partially negative charge, and water, recall from molecular structure, is a bent molecule. So the little white hydrogens here are coming off kind of like little hands, if you will, that could grab on. And if you're to look at any of the white ones, if you can look really closely, you'll see they have partial positive charges because hydrogen tends to have a partially positive end, and then oxygen tends to form negative ions, so it would have a partially negative end, as there is a dipole or an uneven distribution of the electrons here. So if we put this molecule of sodium chloride in, as soon as I release it, the water molecules start surrounding it, and here's what they do. With a soluble salt, they're going to completely pull the sodium and the chloride ions apart. And again, remember I said you're going to have an electrolytic solution anytime you have a soluble salt, a strong acid, a strong base, or even a weak acid or weak base will be a weak electrolyte, but it would make the light bulb glow. You will have conductivity there. Now, if we were to put a sugar molecule in there, let's kind of compare that. So if I take this big chunk of sugar molecule and put it in the water, notice all the water does, because this is 2 sugar molecules, the water simply pulls the sugar molecules apart from one another, but they do not pull the sugar molecule into carbons, hydrogens, and oxygens. So this would be a homogeneous mixture, but it will be a non-electrolyte because there are no mobile ions in solution. Nothing has ionized. So, in thinking about your solubility rules, and we're going to write this down next. This is the notes you're going to take. So in class today, we looked at the types of chemical reactions and we started off with your precipitation reaction. And what we said was that a precipitation reaction, which is also known as a double replacement reaction, is one of our types of reactions that take place in aqueous systems, meaning in water. So anytime two aqueous solutions are mixed, sometimes, not always, but sometimes an insoluble substance will form, and that insoluble substance is referred to as a precipitate. It is a solid that separates out upon standing. So the way that we can abbreviate precipitate is we can use the abbreviation PPT. You could put a S as a subscript with a formula, or you could put an arrow pointing down. So for example, if you were to have a substance that was a precipitate, you would write it with a solid. Usually this is the preferred way, a solid solution. So like lead 2 sulfate, PbSO4, you would see an S written down as a subscript. Now, in order to predict the identity of the precipitates in any double replacement reaction, you've got to memorize your solubility rules for your common salts. So these are some rules you're going to need to memorize. So we're going to be applying them with some examples in class next class. But for now, we're just going to jot those rules down and I'm going to talk you through them on the next slide. But what the solubility of something refers to, when we refer to the solubility, it is the maximum amount of solute that will dissolve in a given quantity of a solvent at a specific temperature. So the solubility of something is determined by the temperature. So obviously if you wanted to be able to dissolve more of something in water or in a solvent, you could increase the temperature and that would allow you a greater dissolving capacity. But when you talk about a saturated solution, then if something is saturated, that means it contains the maximum amount of the solute that will dissolve in that amount of the solvent at a specific temperature. So let's look at our solubility rules. So in this case, we're going to be looking at soluble compounds first, and if they have any exceptions to the rule. And so for this, the first set of rules, Roman numeral 1, soluble compounds, these are substances that when you put them in water, they are going to dissolve 100%. And if there's an exception, that means that it would form a precipitate if any of those substances were present with the ions mentioned. So compounds that contain alkali metals, so remember those are your group 1A metals, sodium ion, lithium ion, potassium ion, rubidium ion, or cesium ion. Those are your 1A metals. Or if it contains the ammonium ion, they're going to always be soluble, meaning they will not form a precipitate, and their formulas would have an AQ written as a subscript instead of an S. There are no exceptions to that rule. These compounds, just like on the animation we just looked at with the sodium chloride, they 100% ionize in solution. So they have a 100% dissociation in solution, and they will all be aqueous. The second rule is the rule that is kind of referring to some of our anions. So if your ionic compound ends in a nitrate, an acetate, a bicarbonate, chlorate, or perchlorate, so you've got to know your polyatomic ions and be able to recognize them. If the salt ends in nitrates, acetates, bicarbonates, chlorates, or perchlorates, they're going to be soluble also, meaning they're going to dissociate 100% as well. There are no exceptions to that rule. Rule 1.3 is the rule about halide ions. So if your salt contains a halide ion, halides are the halogen ions, chloride, bromide, or iodide, then those are going to be soluble, meaning they will be 100% dissociated in solution. Now there are 3 exceptions. So if you happen to have a halide of silver, mercury 1, or lead 2. So this is silver ion, this is the mercury 1 ion, which is a unique ion because it's actually a diatomic. And then you have the lead 2 ion. If you were to have, for example, silver chloride, that would be insoluble. Okay? If you were to have lead 2 chloride, that would be insoluble as well. So these are your exceptions. If your ionic substance contains a halide, bromide, or iodide ion, it's normally going to be soluble or aqueous, except if it has silver, mercury 1, or lead 2 as the cation. Rule number 1.4 under soluble compounds deals with sulfates. So the polyatomic ion sulfate is SO4 negative 2. So if your salt contains sulfate, it is typically going to be soluble, but there are some exceptions to this rule too. If it is containing silver, lead 2, barium, calcium, or strontium, then they're insoluble, so they would precipitate out. Now, I do want to just remind you or kind of point out to you that both of the exceptions for the 3 and 4 here do contain similar ions that might help you remember them. Both of these exceptions have the silver ion in it, and they both have the lead 2 ion in it. Another way I remember with the sulfate rule is barium, calcium, and strontium on your periodic table. If you look at that, they're all in group 2A. And so they're kind of located right near one another. So you've got to have strategies that helps you remember these rules and these exceptions so that you can apply these as we do our predicting products. So make sure that you memorize these rules. I would suggest maybe even making flashcards or writing them out over and over until you learn them. But you do need to have them memorized by heart. All right, so that's the rules for soluble compounds. Let's look at the rules for insoluble. There's 2 of those we're going to look at. So rule number 1 under insoluble says if you have a carbonate, a phosphate, a chromate, or a sulfide in your ionic compound, it is insoluble, meaning they will form a precipitate, they will be solids. Now, there are some exceptions to that rule. The exceptions to the rule happens to kind of refer back to our number 1 rule. Number 1 up here, remember, had no exceptions. So this rule trumps any rule that comes after it because these rules are hierarchical. And so the only exception will be if it has a 1A metal cation or ammonium. So remember, rule number 1 said 1A metal ions and ammonium are always soluble. So that's still going back to rule number 1. The last rule for the solubility rules deals with hydroxide ion. Hydroxide ion is OH negative 1. So hydroxides in an ionic compound are going to be insoluble or form a precipitate unless they contain a 1A metal, ammonium, notice there, and then here we have the barium ion. So if you have barium hydroxide, that's going to be aqueous. Okay, so not solid. So that's your exception to the rule. Now, in class, we're going to take a look at some examples and we're going to apply these rules tomorrow. So just make sure you have these written down and be ready to refer back to them as we will actually go through and complete these examples in class together tomorrow. Now, if you wanted to kind of go ahead and kind of try on your own before class tomorrow just to kind of see, so kind of reinforce if you understand it or not, you can go ahead and give it a shot before class, but otherwise we will be going over these in class tomorrow. Okay, so that's it for the solubility rules. I'll see you later.